Alright, in this video I will finish up the homework problems and move into sample exam number 3. So this was the next problem that I didn't get to in the last video. So we need to do some implicit differentiation, right? I'm going to write x squared plus y squared minus 3x plus 7y equals a. So it says find dy dx. So remember, when we're doing implicit differentiation, we're taking the derivative with respect to x, but when we have to take the derivative with respect to y, we always add this dy dx after it, don't we? Alright, so first the derivative of this is 2x plus the derivative of this is 2y dy dx. The derivative of this is minus 3. The derivative of this last term is plus 7 dy dx, right? Derivative of 8 is 0. So, as we've done in the past, we'll move both terms over that have a dy dx. Okay, so on this side I still have 2x minus 3 equals negative 2y dy dx minus 7 dy dx. And again, our process is now factor out this dy dx. So I'm going to pull out dy dx. This will be negative 2y minus 7 is what's left. So finally, if I divide both sides by this, my final, let's do this, dy, let's see if I can actually erase with the stylus, dy dx is 2x minus 3, 2x minus 3 over negative 2y minus 7. Okay, so we've done a lot of implicit differentiation in this homework, so hopefully it's making sense. Now, the question B, which is on the next slide, asks, I'm going to put this over to the next slide. So we said dy dx equals 2x minus 3, negative 2y minus 7. So remember, one thing we learned last weekend was the curve has horizontal tangents, tangent lines, when numerator is set equal to 0 and solve. Curve has vertical tangent lines when we set the denominator equal to 0 and solve. So for the horizontal, we'll take the numerator, 2x minus, minus 3 is 0. Okay, we're going to add 3, 2x equals 3. So the curve will have horizontal tangent line when x equals 3 over 2. Right? Now, for vertical, let's look at this. We'll set the denominator equal to 0. Notice now we have a y, so this will be the vertical, and kind of says we have two different variables we're looking at. That's y equals 7 over negative 2, or negative 7 over 2. So this is key. This is a really good thing we learned this weekend when we were doing those problems. Curve has horizontal tangents when numerator equals 0. Curve has vertical tangents, right? Because here, slope is 0. Here, slope is undefined. All right? Let's look at the next one. Now I had to go look this up. He wants us to simplify, not take a derivative. So what I learned when I looked this up is that the cosine hyperbolic actually is equal to the e to the x plus e to the negative x over 2. So because our x is natural log of t, we'll say e to the natural log of t plus e to the negative natural log of t. Well, there's a few things to remind you about. First of all, when you have logs, in this case we have a negative 1 in front of that natural log of t. That coefficient can actually be moved up to be an exponent on the t. So negative 1 natural log of t is the same as the natural log of t to the minus 1. Okay? E to the, whoops, I forgot to put over 2. So e to the natural log of t plus e to the natural log of t minus 1 all over 2. The other thing to remember is that e to the x, and natural log of x are inverse functions. So they undo each other. So e to the natural log, of t, since these undo each other, are actually t. Remember, we tested that in our calculator. We took e and we raised it to the natural log of 2, and it equals 2. So what we have here is this first e to the natural log of t. That undoes each other, and I'm left with t. E to the natural log of t to the negative 1, I'm left with t to the negative 1 over 2. Now I'm going to simplify to try to get an answer here. This becomes t to the negative 1, right? That means I change the position of the fraction. That would be 1 over t over 2. I'm going to rewrite these as separate fractions. It's t over 2 plus 1 over t over 2. Right, t over 2 stays the same. If I divide by 2, it's the same as multiplying 1/2, which means 1 over 2t. And to get, I need it over a common denominator. Notice he's got one fraction. My common denominator is 2t, so I'm going to multiply this side by t and this side by t. So I'll have t squared plus 1 over 2t, which is that. Okay? I don't know, did he tell you you need to memorize these for the exam? And maybe the sine hyperbolic, which is very similar? Okay, let's look. We're going to start the sample test. It says compute the derivative, and I like how he says do not simplify your answer. So notice we have to use the quotient rule, right, which is, if it's f over g, f prime g minus g prime f over g squared. So the derivative of the top, derivative of sine is cosine, derivative of x is 1. So the derivative of the top times the bottom minus the top times the derivative of the bottom. Well, the derivative of 2 is 0, isn't it? The derivative of cosine is negative sine. So this becomes negative sine x all over g squared. 2 plus cosine x squared. And I think that's how he'd want you to do it. All right, leave it just like that. Quotient rule, very important. Also knowing the derivative of sine is cosine, the derivative of cosine is negative sine. All right, it says consider this function and determine the intervals where it's increasing and it's concave down. Well, increasing, we need the first derivative. Concave down, we need that second derivative, don't we? So let's start with the first derivative. So if f of x equals x plus natural log of x, derivative of x is 1, derivative of natural log is 1 over x, isn't it? Okay? To figure out where it's increasing, I actually like to figure out where it's 0. Okay? So then I can look at my number line. So if I set this equal to 0, then I get 1 over x equals negative 1. I'm going to cross multiply, okay? Negative x equals 1, x equals negative 1. So on my number line here, I know that at x at negative 1, this is 0, right? The other thing I have to notice here is that I cannot have a 0 in this. So at 0, there's no point because that would be undefined. So then I'm going to test some points, right? The thing to notice too, you see this function, and a reminder about logs. Logs, you can never take the log Never take log of 0 or negative numbers. Okay? So if this original function isn't even available for anything that's 0 or less. So when I look at my thing here, even though this is 0 according to my derivative, I can't use anything except this. Alright, and 0 isn't, like I'm going to do that, 0 is an open circle. We cannot use it. So let's see, as we use positive numbers, what this derivative is going to look like, right? And guess what? 1 plus 1 over x is always positive if x is positive, right? So it looks like the interval where this thing is increasing, it's going to be always increasing, starting at 0, not including, up to infinity. Right? We cannot use the lower part of the graph there. So it's always positive, always increasing. Let's look at the second derivative now, because we want to look at concave down. So here's the first derivative, 1 plus, now 1 over x I can rewrite as x to the minus 1, can't I? Second derivative, derivative of 1 is 0. We use the power rule on this, negative x to the minus 2, which is the same as negative 1 over x squared, isn't it? Okay, well, guess what? This thing can never be 0. There's no x that I can use that will be 0, that can make this 0. So that means there's no inflection point, right? I can't set it equal to 0 and solve. And the other thing I notice is we know that x squared is always, I'm going to say 0 or and positive, but here it can't even be 0. So in this case, x squared is always positive, isn't it? Whoops. X squared is always positive. And remember, the domain up here of the original graph had to be x greater than 0. So we're looking over here, and anytime I use a positive x in here, this thing will always be negative because of that negative sign. So since it's always negative, it's always concave down, right? So some of these, we're not, I keep doing that, we're not actually doing a calculation per se. We're looking at what we're given and drawing some conclusions from it, right? We know anything squared is always positive. And in this case, if this is always positive, this thing's going to always be negative, so it's always concave down. But we did have to consider the domain of the original function, right? Okay. And if you graphed this thing on your calculator, you'll see both of what we had there. It's always increasing and it's always concave down. All right, next one. All right, we're looking at a composition of functions, right? So let's first take our composition of functions and take the derivative of. So I'm going to take the derivative with respect to x of this thing. So using the chain rule, I take the derivative of the outside, so it would be f prime, g stays the same, times the derivative of the inside, g prime of x. Now this just means you're evaluating at x equals 4. I hope you made that clear. So if I'm evaluating at x equals 4, I take this derivative, f prime of g of 4 times g prime of 4, right? So g of 4 is 2, so that means f prime of 2 times g prime of 4 is 3. All right, f prime of 2 is 5, so that's 5 times 3. Oh, geez, on my sheet I wrote plus. No, these are times, definitely, using the chain rule, right? Yep, so that answer is 15. But write this out to help you see what to fill in. It's simply the chain rule. It just looks a little tougher when we have these f's and g's in there. All right? Now I'm going to stop here and continue on the third video.